Okay. Oh, what I forgot. I should talk because this really may come into play today. I can tell, or this semester, the second chance thing. Have you heard of this? Have you been in a class with a teacher who did this? So, yeah. There you go. That's a good way to put the timeout chair. Okay, I shouldn't. Yes. So one of the new things that you'll be hearing about is the yes. So students who are disruptive and unruly and whatever. There's a series of interventions and so forth. And so one of those interventions is the second chance room. So if somebody in Mr. Boyd's class is, you just can't handle it or whatever. So at some point, somebody may come in the room and sit down in that chair right up there and have to sit there and fill out the form. You got a whole form you have to fill out, reflect on how bad you were. And so the timeout chair is very good. It's not supposed to be. It's because here's the rule is if they come in, the principal even said if they come into that second room and they so much as high five another student, they walk in and their buddies are yay, then they're out. Then they go to the office and it's for whatever. So it shouldn't be an issue, but Mr. Boyd and I kind of have a path to meet one train. So I think we'll be fine unless I just want to do it for fun. So yeah. So it happens in here. Yeah, if you guys get to the point I just can't handle it, I'll have to send you a So anyway, but I joke about it, but last semester my third block class was Algebra 1B, sophomores, and trust me, I had some days where, now typically I send out the high top table over there, I just make them sit in the hall. As a kid, whatever, you just got to get them out of the room. So anyway, I don't anticipate that being a problem. Now this semester I've got these two calculus classes, and then I have an honors advanced math class. So I'm hoping that's not going to be an issue, but we'll see. But anyway, so there you go. So that's what. So if somebody comes walking in over here, I don't think it's going to happen. He does have freshmen, so you never know. That's what's going on. But you may be in some classes where maybe you might see more of that. You never know. All right, so let's go here. We're on page 209 in the book. If you want to follow along, but that's where we're gonna. That's what we're talking about today. It's section 4.1, first part of section 4. Now remember, we did 4.2. That was the L'Hopital's rule and the limits. Okay, before break. There's really no particular order that you have to do chapter 4. Remember what I said is that chapter 4 is just about different ways to use the derivative. So it's really just a bunch of separate, discrete sections that the only thing they really have in common is somehow they involve the derivative. Somehow they involve using the derivative. Okay? So, section 4.1, what we're going to do here is differential equations. Now, we're not going to do, this won't show up on a quiz, other than at the end of this chapter, we have what I call a no calculator quiz, which is just about the ideas of this chapter. And so it'll show up a little bit there in maybe a matching, you'll see what I mean, a matching situation or something on that quiz. We may have to do something with differential equations there. Okay? So let's review. So differential equations is something we've talked about. Okay? So there's two important things about differential equations. First of all, what is a differential equation? Think of the two words that make it up. A differential equation. It's an equation that contains derivatives. Okay? So first thing we just got to understand is what is a differential equation, right? This is stuff from before, right? So this part is not new. Okay? So good review. We did this in chapter 2. Differential equations, an equation that has derivatives in it. So y prime equals 3x, that would be a differential equation. Okay, and we talked about different types of differential equations, right? We can solve it. Okay, we'll get into that in a minute. Okay, second thing, what's the solution to a differential equation? The original function. Okay, it's not a number. It's not like x equals 4. You know, in algebra class, when you solve, or in trig, when you solve an equation, you get a number, like pi halves or 7 or whatever. Maybe you get multiple solutions, right? Differential equation, the solution is another function, the original function, y or f or whatever. Okay, without any derivatives in it. Okay, all right. So those are two important things. And then we had three different types. There's the type we could just simply solve using an antiderivative. We did that on the last quiz when we gave you a velocity function and then had you find the position function. That was solving that differential equation, because technically a velocity function is a differential equation because the velocity is a derivative. So it's like p prime equals, right? So it's technically a velocity function in that case is a differential equation, right? We didn't use that lingo during that problem, but that's what was going on. So we just take the antiderivative, stick on a plus c. Okay. The only time we can do that, though, is when there's only the x or the t, the input variable, on this other side. There's not any y's in there, y double primes or something. Okay. Then there's a type where we could just memorize the solution. Now we're going to work on this second one here today. We already had done this one earlier. This was just number one here was just your temperature, like exponential growth of money, like bank interest, okay, something like that. Okay, y prime equals k times y, the solution, that's y equals a e to the kt, it's just exponential growth. This is the one we're going to work with in this section. It's called Newton's Law of Cooling. Now, I think I've already talked about it a little bit. We talked about a cup of coffee cooling in the room, that kind of thing. Okay, and that's the solution to that. So we're going to be working with this a lot today, right here. Okay, we'll be working with this equation right here. That's the solution to this differential equation right here. Okay? And if you remember what we said about that, okay, why is this Newton's Law of Cooling? Because y is the temperature of the coffee, t is the temperature of the room, so it's going to be a constant. The greater that difference, the faster it'll cool. So the bigger this side is, the bigger the rate of change is. The smaller this gets, the closer it gets to room temperature, this number gets smaller, so the rate of change gets smaller. So it just comes down and right at room temperature, just like that. Okay, so it's an exponential k kind of situation. Okay, all right. And then the third type was just the type we can't solve, but we could verify. Remember the t-chart? We could verify that something is a solution. Okay. And now here's the new thing that we're going to do today. So all that so far has been reviewed. The new thing is we're going to approximate the solution graphically by doing what's called a slope field. Okay? So that's going to be the new thing we do today. Approximate the solution. Remember the solution is what again? The original function. We're going to approximate that solution graphically. And it's called a slope field. Okay? All right. Now, if you think about that, let me see what I got. Okay. So let's do this first. Let's do this first. Let's do Newton's Law of Cooling, and then we'll move on to the slope field. Okay? Those are the two kind of new things that we're kind of adding here on differential equations. All right, so Newton's Law of Cooling. Okay, so Newton's Law of Cooling is this differential equation. It's not surprising then that the solution just looks like a basic exponential shifted up to room temperature. Now, it wouldn't always just have to be, this differential equation wouldn't just have to be about, cooling liquids, but that's kind of the most famous application. Okay, but it's just a basic exponential shifted up. Now it's exponential decay, so that tells you the k in here is going to be negative, right? The k in here is going to be negative because this should be positive right here, right? Because I think we had this on an earlier quiz, didn't we? Where you had to say if the K was positive or negative, right? Because this is the temperature of the coffee, this is the temperature of the room, this should be bigger than this, so this should be positive. And then, but it's the temperature is going down, so Y prime should be negative. So therefore the K is going to be negative. So if the K is negative in an exponential, you get decay, you get that kind of a shape. Okay. So that's what's going on. So that's the basic part of that. The key to Newton's law of cooling is this is what we're going to work with, right? So really, this is pretty easy. Problems that involve this, and this, so this probably won't show up on a quiz in here until maybe the midterm. Maybe you have to do something with it on the midterm, because I'm only going to do stuff at the end of the chapter on a no calculator thing we're doing. So you would have to use a calculator for this problem. So we'll do some homework with it, but we're not going to do a quiz on it. All right, so let's go through a problem though. You're going to have a homework problem that's going to be very similar to this scenario. So let's walk through it together. Okay, so we got hot coffee, 190 degrees. The room temperature is 70 degrees. After 4 minutes, we take a measurement, and the coffee is down to 170. Okay, so a couple of questions we might be interested in: how hot is it going to be after 9 minutes, and how long till it gets down to 100? Okay, those could be a couple of things we'd be interested in. Well, since we know this is a Newton's law of cooling situation, we can jump right into our equation. Okay, so what known value did I plug in already? Big T, right? Big T is the room temperature. So that goes there. So we got big T plus A e to the KT. Now the other two values I don't know. I don't know what A is, and I don't know what K is. Okay? But there's information. So what we have here is kind of like an initial value problem, essentially. Right? What I've done is I've given you some initial conditions right here and right here. Okay, now the word initial is a little deceiving. Initial, really, you think at the beginning, but we call both of those initial conditions. Okay. So what am I going to plug where? Let's start with this one. What can I plug where with this scenario right here? Y would be 190. What about here? Little t would be 0 at the beginning, right? And that's nice because when you put a 0 into here, you're going to get e to the 0, which is 1. So you're going to get a, right? You're going to get e to the 0. So this is where if you were thinking to put the 190 in for the a, see, that's not right. Okay, and that's because in bank interest we always talk about that a was the initial value. Well, it is if t is 0. Okay, but the 190 goes here, the 0 goes in there, and so we get 190 equals this, e to the 0 is 1, so a is equal to 120. Okay, a is equal to 120. Then, so now we've got this. Okay, so now we've made a step further. We found our a value. Okay, now we take this one. And what goes where? Where's the 170 go? In for y. And the 4 goes in for t. Okay, so 70 plus 120 e to the 4k. Now, here's where I would just get my calculator out and do a solve. Okay, I would just do a solve. I mean, yeah, you could subtract 70, you can divide by 120, you can get it in terms of LNs and stuff like that. Actually, your calculator will probably give it to you in terms of LNs, which is fine. Okay, there's no need to go to a decimal. You could leave this as an LN number if you want. Okay, you don't have to go to a decimal. But if you do, make sure to write out plenty of decimal places because we're not done yet. We haven't answered either of the two questions yet. But what we do have is an equation. Now we can take this value, so we found the a now and we found the k. So now we have our solution. Now we have our basic equation we can work with. So you're going to go through a problem very similar to this. Okay? All right. So now that's our k value. Okay, so for this particular cup of coffee, this is what's going on. Now let's talk about this a minute. The k value is determined by the cooling, whatever the liquid is, I think the problem you're going to do in your homework is there going to be two different cups. One's going to be like a ceramic mug. One's going to be a styrofoam. So the styrofoam would be a better insulator, right? So it's going to have, so that situation would have a different K value, right? Than the situation in the ceramic mug, right? And so then you're going to compare. You're going to compare those scenarios. Okay, so you have two different equations going on. So for this equation, if we put a different cup of coffee, if we did put a cooler cup of coffee, the K value wouldn't change, right? Or if we change the room temperature, the K value wouldn't change, okay? Because if it's in that same cup and so forth, okay? But so anyway, for this scenario, we would have this. Okay, so what is it after 9 minutes? Pretty simple. You just put a 9 in there, and you get your temperature. Okay, so the first question was how hot is it after 9 minutes? You plug a 9 in for T, okay, and you got that. All right, and how long does it take to be 100? You just take your equation, set it equal to 100, get on your calculator and do a solve. Okay, and I think it comes out to be 30.414 minutes. And those are basically the two kind of things you can do. You're either going to plug in for T or plug in for the Y, and you're going to find the other. Okay, so it's pretty simple. It's pretty simple to use. I mean, there's really not much calculus there. The only calculus is the differential equation idea, that it came from this differential equation. But once we know what the solution is, now it's just an equation for it, right? And now it's just an equation for the temperature of the coffee. We find some initial conditions, and we plug it. So pretty simple thing. Okay, from that standpoint. All right. But just understand, anytime you get a situation that sounds like it's a cooling, a Newton's cooling situation, the key is you got to memorize. You got to memorize, that's your equation. So if there's anything you really need to study up on, just understand these two things. Okay, this is the one we work with. It comes from this differential equation. All right, let's move on to the slope field idea. Okay, so you'll have some homework on that, Newton's law of cooling. Then the other part of the homework is going to be this idea here, called slope fields. A slope field is a graphical approximation to the solution. And remember, solution means original function. Right, like y. So basically what this is we're going to get a graph of y. Okay, what we did in that in Newton's law of cooling, we did an equation for y. So our solution was an equation of the original function. Slope field is going to be a graph of the original function. So it's still a solution. It's still finding the original function. It's just finding a graph of the original function. But it's only going to be an approximation, and you're going to see why here in a minute. All right. I would propose to you that we have already done this. And we did this in chapter 1. Remember when I gave you an F prime graph? I told you to draw the F graph? Right? Isn't that solving a differential equation? That's not an equation. Okay? It's not an equation, so I guess you could say it. But essentially that's what it is. You're starting with the derivative, and you're wanting to find the original function. Okay? So all the slope field is a better version of what we did back in chapter. That's okay, just a better version. So let's go through that. How did we do this? Well, what did we do? Let's see if we can remember. First of all, I said, well, where do I start? Well, where should I start? Oh, we don't know. That's the what? The plus C, right? That's that vertical shift. Remember the plus C, when you do an antiderivative, it's at plus C. We don't know where to start. Okay? Well, here's what I'm going to look at. This graph is mostly above the x-axis. What's that mean? The graph I'm about to draw is going to be increasing, right? F prime, since F prime is mostly positive, F is going to be mostly increasing, so maybe I'll start down here. Okay? All right, but it wouldn't really matter. All right, so what happens? I notice this is positive and getting more positive until then. Remember, these y values are the slopes of down here, right? So what's this graph got to be doing? Concave up. When F prime is increasing, F has to be concave up, right? So when this is increasing, this got to be concave up. So it's got to be going like so, okay? Okay, so this point is going to match up with that point right there, correct? And what is that point? Inflection point. Didn't we say that the max and mins on F prime, aren't those always inflection points on F? Okay, right? Kind of coming back to you a little bit with the chart, right? The max and mins here on F prime ended up being inflection points here, but anyway, this is concave up. Now, as this is positive but getting less positive, that means this graph is going up, but leveling, right? Well, it's not zero though, right? But it's concave down, right? Now, I shouldn't have made that look like a slope of zero because it's not a slope of zero, right? This is not down here of zero, so I shouldn't have leveled that out quite so much. But it's going up, but it's concave down, okay? Like so. Okay, now look, now it's back to positive and getting more positive, so it switches again to concave up, right? So I got an inflection point there, an inflection point there, an inflection point there, and now what do I got? I got positive and getting less positive, and actually a slope of zero at this point, right? This is, remember when we did that? That's going to be a local max, isn't it? That's going to be a local max right there. And now we got negative and getting more negative, so it's concave down, negative slopes getting more negative, and then negative and getting less negative, and actually leveling off, because that's back to zero, so that's a slope of zero, something like that. Right? Okay? So, now, here's why slope fields are going to be better, because that was really rough. I mean, all I didn't really know how fast this was going up. In other words, if I ask you right now, and let's just put some numbers on here, 1, 2, 3, 1, 2, 3, 4. If I ask you right now, give me an approximation of f of 3. I mean, think what we just did with the coffee problem. I asked you for y of 9, right, or f of 9, or y of 9, right? And we had an equation we could really plug in. We said, man, the coffee's going to be this temperature, 149 point blah, 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 at this time. It's very exact, because we had an equation, right? If I ask you right now what's f of 3, how confident would you be in that y value? Yeah, it's awful. Well, number one, I didn't know where to start, so we didn't have a c value. But let's say we did know where to start. I still would not be very kind. Look at that thing. It's awful. Right? I mean, I just went up for a while, and then I went this way, and then I had no idea how steeply you go. I didn't have any of that. So I'm not very confident at all in those actual f values. Okay? Shape of the graph, pretty confident in that. But other than that, not very good. Okay, so slope field is going to be like this, but a better version. Okay? All right, so here we go. So, go ahead and draw this on your paper. I'll give you a minute to do that. Now, you're not going to have to draw your own graphs like this very often. Tomorrow, I'm going to give you a worksheet, and you're going to do some. Okay, on today's homework, I think it's going to be more about matching some graphs. Okay, but I'm going to show you on the AP test, it's not every year, but many years, one of the 6 free response questions is to sketch a slope field. And they give you a graph like this. Now, it doesn't have quite this many dots on it usually. Okay? But at the end of this chapter, I may have you sketch one. We'll see. Okay? So all I've done is I've just put dots at all. It's just like having graph paper, but I just put dots at the different marks here. Let me put a grid up here. I'm not sure. So I've got some graph paper if we need to do it. No, my grid's not matching. Now, the calculator will do slope fields, but you can't get real exact with like where the dots are and where the things are. You'll see that here. So we're probably not going to spend much time doing it. And on the AP test, they never ask you to do anything with the slope field on your calculator, so it's not really something. Okay, but this is essentially plotting points. Okay, it's essentially plotting points. Now here's my differential equation. So I would want to label this y, this would be t. Okay, so the graph I'm looking for is the original function y. Okay, here's my differential equation, y prime equals 2t minus 1. Now it's one of those that we could solve, right? What do we know the equation's going to be of this? T squared minus 1t plus some c. So what shape should we end up with here? We should end up with a parabola, right? We should end up with a parabola. Okay, so anyway, but let's pretend, but it could have been 1, this could have been y prime equals 2y minus 1. And then we couldn't have done that, right? And then we would have no idea what the solution was, okay? But we could still do what we're about to do. And what we're about to do is plot points. So what I'm going to do is I'm going to plot points in here. So I'm going to let t equal 0. So if I let t equal 0, what do I get in this equation? I get y prime equals, plug a 0 in. What do you get? Negative 1, right? So I put a 0 in for t. 2 times 0, 0 minus 1 is negative 1. I get y prime equals negative 1. What's y prime mean? Slope. So what I know is whenever t is 0, my slope has to be, the slope of my graph has to be negative 1. So here's what I'm going to do. These are called slope segments. When is t 0? That's right here on this y-axis, right? Right? T is 0 right here on the y-axis. So everywhere I have a dot on the y-axis, I know my y-graph is going to have to come through here and have a slope of negative 1. 45 degrees, right? Make sense? Now I keep doing this, and I'm going to get kind of a picture of the graph. So let's keep going. So what about when t is 1? Plug a 1 in for t. What do you get? You get y prime equals 1. So when t is 1, which would be on this vertical column, when t is 1, I'm going to get a slope of 1. Again, 45 degrees, like so. Right? I guess I did need this one down here. What about when t is 2? Y prime is 3. 2 times 2 is 4. 4 minus 1 is 3. Y prime is 3. So when t is 2, I'm going to get a slope of 3. So it's going to be pretty darn steep. Now, so what I have here is columns of segments that are exactly the same, right? Because the only variable that's in my differential equation is t, right? And so what I'm getting is columns that are exactly the same because t doesn't change in a column. Let's go over here to negative 1. When t is negative 1, what's y prime? Negative 3. Now you don't have to write this down, what I'm writing here. I'm just doing that to help you see it this first time. But you can just do this in your head. So when t is negative 1, the slope's going to be negative 3. So I know the graph is going to be coming down through there steeply, like so. All right, now, so where do you suppose the vertex of this parabola is? 1/2, probably, right? Because we have slope negative 1 to 1, because of symmetry. But can't you see a parabola there? Right? Can't you just, if you squint, you kind of step back, right? You can see that parabola. Okay, now, what can I add to this problem? What I could have added to this problem is made it an IVP, an initial value problem, which means you just bring in an initial condition. So what if I said y of 2 is 1? So what if in the original problem I had given you this and then told you that? Well, what would you do? Plot that point, right? So y of 2 is 1, so that tells me that the parabola's got to go through there. So now what do? I say go with the flow. We're going to draw the actual solution. The red is not the parabola, right? The red is just the field that the parabola is going to be in, right? We need an initial condition to know where. So once I get the initial condition, I know it's going to go there. So now I'm just going to go with the flow. I'm going to come down here. Now it's rough. It's still rough, but isn't it better than the other one we did a minute ago? It's definitely better, okay? Now I'm just going to kind of go with the flow of those segments. And it comes through here, and I know it's going to level off because then I got to get back to here, and then it's going to get steeper, and then, you know, whatever. Something like this. Now, I do know there's some symmetry, so I probably do have, it probably is going to hit that point, but I don't have to be that exact. And then it's just going to get steeper and steeper, and there we go. And now it just fits right in there. Go with the flow. So one of the things I might do is give you a slope field, and then give you an initial condition and say, now sketch in the slope field. So you just plot that point, and you just go with the flow. Go with the flow of the slope field. Okay? So, a little more work, but it's a better representation of the solution. Okay? Now, we knew it was going to be a parabola. Okay? But, again, if this would have been 2y minus 1, who knows what kind of thing it would have been. Okay. Now, let's look at, this was on the AP test in 2015, actually the international version of the AP test. Okay, now I don't know, it's up to you whether you want to jot this one down or not. But this was one of the 6 free response questions. Now, they went on to ask some other questions about this, this differential equation. Now remember, dy over dx is the same as what? Y prime, right? That's just y prime. So we got x, y minus 1 over 4, right? Same thing. And so, let's go ahead and do it. Okay, now the difference here is, it was pretty easy on that last one, because when I put a 0 in for t, that's the only thing I had to plug in, that gave me a whole column worth of slopes. Problem here is it's going to change, because it's got both x and y in it. So I can't just put a 1 in for x, I have to put something in for x and for y. So I have to actually individually plot all 12 of these points. Okay, so let's just start down here, negative 1, 0. So negative 1, 0, what would I get? 1/4. So that's pretty small slope, right? 0, 0. What do you get? 0. 0 slope. 1, 0. Negative 1/4. Okay? Let's go up here. Negative 1, 1. Negative 1, 1. 0. 0, 1. 0. Matter of fact, every time x is 0, you start getting some shortcuts, right? Every time x is 0, this is going to be 0. So you can tell, right? Every time x is 0, this is going to be 0. So that helps a little bit. 1, 1. See, oh, and every time y is 1, it's going to be 0. Well, I guess that's my last one, so doesn't matter. Okay, so those are 0. So that's pretty easy so far. Negative 1, 2. So negative 1 and 2. Negative 1/4. So again, pretty shallow. Okay, let's go to 1, 2. That'd be 1/4. Okay, and finally negative 1, 3. Negative 1 and 3. Negative 1/2. So a little steeper, and then this would be positive 1/2. 1, 3. That'd be 1 times 2, 2/4. 1/2. Okay, that one wasn't too interesting. A lot of zeros. Okay, so there's not much. That one's a little harder to see, like, what's the solution curve? The more little segments you have, the easier it is to see what the solution curve looks like. That's a problem with doing it by hand. It just takes a long time. So we're not going to spend much time doing it by hand. Okay, tomorrow I'm going to give you a handful of them so you get the hang of it a little bit. Okay, we're going to spend a ton of time doing that. But you're going to see a lot of different variations of differential equations. But so understand that we just saw one that had a t in it only, and all the columns were the same slopes. Here you don't see that. These all change. Here you got a positive slope, 0, negative, getting more negative. Now this column's the same, but here it's negative, 0, positive, getting more positive, right? And so we're also going to see rows where they don't change, and that's if you only have a y in. Okay, so matter of fact, it might be a good time to just talk about that. Let's go back to this. Okay, so yeah, we're basically ready to do the homework. But we could say this: if your differential equation is y prime with x's only, you're going to have columns of slopes that are going to be the same. If you have a y prime that has only y's in it, okay, that's an apostrophe, by the way. Those are apostrophes. I don't know if you want to write this down, but if you have only y's in it, what you're going to do is you're going to get, you're going to get rows of slopes that are always the same. And if you have y prime equals, and then it's got x's, and it's got y's, then who knows? I mean, it's just, you don't have, I mean, it's just going to be, you're going to have slope segments all over the place. Now, why do I tell you this? Because what you're going to do on your homework, you're going to do a matching activity. They're going to give you some differential equations, they're going to give you some slope fields, and you're going to match them. Yeah, you can do that by plotting some points, but you can narrow down your choices if you understand this. If every time you plug in a new x, you get a slope, and every one of those x's is going to be that same slope, you're going to have columns of, okay, kind of like, I suppose it's a lot like in algebra class if you graph an x equals, right? If your equation just has x in it, it's a vertical line. If your equation just has y in it, y equals 4, it's horizontal line. Well, it'd be the kind of same thing here. If your differential equation just has y's in it, it's going to be like this, okay? So, let's look in your book and you'll get an idea of what I'm talking about. So go to page 217. Go to page 217. Well, maybe, I tell you what, go back to 211. Go back to page 211. Okay, and so you can just see some different slope fields. Okay, so look at the bottom of page 211. At the bottom of page 211, you can kind of see an exponential in there, right? If you look above the x-axis, you can kind of see an exponential. And if you look below the x-axis, you can see an exponential, but it's going down, right? You kind of see it in there. You can kind of see the x-axis is kind of a horizontal asymptote. Okay, and you turn the page, and sure enough, they've drawn some different ones in there. Now, those are all different solution curves depending on what your initial condition is. You change your initial condition, would tell you which one of those branches you would get. Okay? Now, it's kind of hard to see on the next two down on page 212, but you got a parabola on the left, so they got a bunch of different parabolas drawn in there. But then you look at the one on the right, and that one has both a y and an x in it, or they use t, a y and a t. And so notice it's kind of a diagonal, and it's kind of going all over the place. Okay? Turn to page 217 now. Let's turn to page 217. So you see those slope fields down the side. Okay? Look at those 4 on page 217. Tell me which one of those has only x's in it. Which one of those differential equations is just going to have an x or a t? 7, 8, 9, or 10? Number 8, right? Because as you go down number 8, you've got these columns of slopes that never change. Okay? So that's going to be one that just has an x in it, or a t, I guess, is what it is. Now, what about 7, 9, and 10? Do those have columns that never change? No. Do they have rows going across that never change? No. So that tells you 7, 9, and 10 are going to be differential equations that are going to have both x and y, because every time either x or y changes, the slope changes. Okay? Turn the page. Do you see any of them there that are going to have just a y in the differential equation? Are there any of those that when you go across horizontally have segments that always have the same slope? Doesn't 13? Doesn't 12? 12 and 13. Okay, so are you seeing that? Now again, you can do these without this knowledge, but it makes it way easier. Because if you can eliminate, you can make the matching go way better. Then you can just plot a few points and see which ones match the slope you're looking for. 12 and 13, if you go across any row, you see segments that never change. What that means is every time you move to a new y up and down, you get a new slope. But when you go across, when the x's change, it doesn't matter, right? That's what's happening. When you go across, that's when the x's are changing. You don't get new slopes. There are no x's in the problem, only y. Okay, so 12 and 13, you know, are only going to have y's in it. 11, what about 11? Just x's. But 11, they're vertical columns of slopes that never change. That one's going to have only x's in it. And then 14, what's 14 going to have in it? Both x's and y's, because the vertical columns, the slopes change as you go up and down, and across, the slopes change as you go across too. So it's going to have both x's and y's. So if you can do a little bit of that, eliminating your business. Okay, so your homework, if you still have your homework sheet from before, it's the top line, the 4.1, okay? 3 through 14 are basically these questions about slope fields, and there's some matching you have to do in there, okay? Matter of fact, let's just do number 3 together so you kind of understand what they're saying there. Okay, so this will be on page 217. Okay, but we've got 3 through 14, and then we've got 23 and 24. Now 23 is probably the one that's going to take you the longest. That's a whole kind of new, 23 and 24 both are Newton's law of cooling. So you're going to go through that whole process we did with the, here's the initial temperature of the coffee and so forth, so on. Okay, so you'll use your calculator a lot for that one. Okay. All right, so number 3 says, and so 3, 4, 5, and 6 are all very similar. So 3 says, all right, you have this differential equation. Okay, this is one of those we'd never be able to solve. They say that f is the solution, so in other words, your original y. Okay, they tell you that f of 1 is 2. I would probably prefer to say y of 1 is 2. Same thing. Y, f is the solution, means that's y. F and y are interchangeable, really, in this problem. Okay? Explain why y equals 3t minus 1 is the equation of the tangent line at the point 1, 2. Well, I say, the heck with that. Let show that it is. Let's just do the work of finding the equation of the tangent line. And of course, this is that question that I still can't figure out how to teach well, but when you have to write the equation of a tangent line, what do you need? Point and slope, right? You need a point and a slope. So what do I need? I need a point and I need a slope. Now, in this case, I really need a t there and not an x, okay, for this problem. All right, I really need a t there, not an x. But I need a point and a slope. I want to write the equation of a tangent line to the y graph. So I need a point and a slope. Well, what point do I know? 1, 2. Okay, well, that's easy. And so now what do I need? Slope. Gosh, if there was just something there that would give me the slope. What? What gives me the slope? The differential equation. That's what it gives me. It's the derivative. It gives me the slope. So all I have to do is plug in a 1 and a 2 and a 1 right there. 1 squared times 2 is 2. 2 plus 1 is 3. There's my slope, right? I just plug it into the differential equation. So now I work it out. 3t minus. Now, normally I'd let you just stop there, but the problem says show that this is it. So, okay, I'll go ahead and finish it. And I get that. And I said, sure enough, y equals 3t minus 1. And that work is my show. And there it is. Okay, so you don't get all hung up on that one. It's very simple, right? They give you a point and they say, you know, equation tangent line. But normally what we do is just plug in the 1, 2, get our slope, maybe do a slope field, whatever. But right now it's just that. Okay, so there's your homework right there.